Hey guys, today we're going to talk about early atomic models. So the first atomic model came up back in ancient Greek times, and Democritus was the person who decided that all matter consists of small spheres called atoms. He thought that atoms could not be made into smaller parts, and that all spheres were completely identical. So he is what I'd like to signify or give you the cheat sheet of being the solid sphere guy. He thinks everything is made of solid spheres, and every single element or atom looked exactly like the atom next to it. So this may be hydrogen, this may be sodium, and this may be cesium. So every single atom is exactly identical. Dalton had a little bit more detailed of an idea. He agreed with Democritus and said that all matter consists of small spheres called atoms. He agreed that all matter or atoms could not be made into smaller parts, but he differed because he thinks that all atoms of each element have a different mass from each other. So like in the last slide, if this was helium, sodium would be much bigger because sodium has a larger mass than helium. So we still have the solid sphere idea, but each element has a distinct mass. Additionally, he stated that all atoms of each element have a specific chemical behavior, meaning hydrogen acts a little bit differently than chlorine acts, calcium acts a little bit differently than bromine acts. Each atom has a specific characteristic or behavior that they follow through with. And we can always find the compounds because they have the same mass ratio. H2O always has a mass of 18 atomic mass units. So whenever we see 18 and it acts the same way, we know it's H2O. That's how he determined if we had compounds or single substances. So compounds were found because they always had the same ratio of mass and they acted the same way. Thomson is the next major atomic model. He thinks that all matter consists of tiny spheres, and each tiny sphere has a specific mass, so the same ideas that Dalton shared. But now he thinks that each sphere can be broken down into positive and negatively charged parts. So this diagram on the top left, this is an example of what J.J. Thomson thought. The red in the background was a positively charged pudding, is what he called it. And these little tiny negatives, these are the plums that are in that pudding that hold a negative overall charge. So the pudding has a positive charge, the plums floating around have a negative charge. Now when we call this the plum pudding model, that's because that was a generational thing. In his era, plum pudding was normal. We could also call this the chocolate chip cookie model or the tapioca pudding model. So in the chocolate chip cookie, the red is the actual cookie piece. That's the dough of the cookie. And the negatives, or the electrons, those are the chocolate chips floating around in it. Overall, these atoms are neutrally charged because the positives and the negatives cancel out, but they do have individual parts that are positive by themselves or negative by themselves. Rutherford was the next guy. He thought that all atoms have high-density, positively charged center surrounded by a negatively charged electron cloud. This is a brand new way of thinking because everyone in the past has thought that the atom was just a solid sphere. He's saying it's not a solid sphere. It has a pinpoint center that is super high density, but the majority of it is completely free and empty space with electrons zooming around. This means that there's areas of high density of charge and most of the mass right in the center of the nucleus. And he determined this using his gold foil experiment. So he's the crazy electron cloud guy. This center part right here is the positively charged nucleus with most of the mass of the atom, and these blue circles with the red electrons, that's the electron cloud. So his gold foil experiment was super fancy, and this was the way that he determined that this happened. He set up a piece of gold foil right here in the center of a semicircle, and this circle is zinc-coated metal. And the reason why he used zinc was because when alpha particles hit it, it actually let off a glow. So this was our little particle shooter, and he shot the alpha particles in towards that gold foil. And what happened, there were some scenarios where as he shot it in, the electrons bounced back where they came from, or they bounced at an angle towards the outside of the circle, but in most of the scenarios, they went on one of these paths. Either the electron shot straight through and didn't touch anything, or it veered and ricocheted off to the right or to the left. So when you think about atoms, and if you think about them being solid spheres, we would essentially have a wall of solid spheres in that gold foil. And when we shoot a particle at it, when it hits that wall, logically we would think it would bounce backwards. It might ricochet a little bit because they're spheres and they're going to have a little bit of curvature to them, but it's not going to go straight through. Since most of the particles did, Rutherford was able to decide that he would have this high-density nucleus with this crazy electron cloud, and another high-density nucleus with another crazy electron cloud. And when he shoots the particles, if they go straight through the middle, they're going to go straight through to the other side. If they go close to that nucleus, they're going to veer to the right or to the left. So instead of these solid sphere walls, we have these walls that have a high density area right in the middle, but mostly clear space around them. So in Thomson's experiment, if we would have done this with the particles would have followed straight through, because that entire substance had a neutral charge. The positives and the negatives canceled out. But in Rutherford's experiment, these blue particles are the electrons. When the particle gets really close and hits head-on to that nucleus, it bounces backwards. When it gets close but slightly further away, it only ricochets off to the side. So this means that this center has to have a positive charge, and that positive charge is going to reject or reflect these positive particles, because like charges do not go well together. Bohr is our last model that we're going to look at. He agrees with Rutherford and thinks that all atoms have a high-density positively charged center surrounded by a negatively charged electron cloud. But he disagrees because he thinks that the clouds are not really clouds at all, but they're more like planetary orbits. So essentially those electrons have an orbit or a circle that they follow at all times. They can jump between circles, but instead of having that crazy pattern that's going in no logical form, he thinks that electrons have just one path that they follow as they rotate, and one path as they rotate. Now he believes this because he was able to add energy to electrons, see them jump in energy level, and fall back down and release that energy again. So he made this educated guess, or this hypothesis, by doing experiments and noting and making observations of what occurred during those experiments. Today we actually have a little bit of both models, Rutherford and Bohr, as our current model. So as an example, we have that high positively charged nucleus, and instead of having a perfectly circular planetary orbit, it kind of follows this weebly-wobbly pattern. We can have the electron anywhere on this path at any given time. It is still a fixed orbit, it's just not perfectly circular. And then the next one goes a little bit farther out, still a fixed orbit, not really perfectly circular. So it's a little bit of both. We are going to actually use the Bohr model in class because it's easier to see, easier to draw, easier to understand. But I do want you to know that we have made some steps since then, and the newest model is a mixture of both. So I'll see you tomorrow where we can talk about the atomic models and see if we can identify which one is which and work a little bit more in depth with the Bohr model. So I'll see you tomorrow.